Now on to the angular velocity. So what we're going to do now is we're going to generate an angle by rotating our radius phasor at a constant speed. So that constant speed is the angular velocity. And you can think of that angular velocity like the frequency on the sine wave. So on the circle itself, if we take that phasor and spin it slower, it will relate to a slower frequency or a lower frequency on the sine wave. If we rotate it faster, we end up with a higher frequency. So you can think of it in terms of at a lower frequency and a slower angular velocity, the sine wave stretches out and its iterations or its alternations are slower. As we speed up the angular velocity, the frequency starts to compress because it gets higher and there are more cycles per second. So the angular velocity is measured in radians per second or in degrees per second. So if we cram more radians per second in there, we're going to have a higher frequency. The symbol for angular velocity is omega. We use the Greek letter omega, which what looks like a little tiny w. And omega is equal to 2 pi times the frequency. Why the 2 pi? Because it's periodic. It happens over and over and over again. And so the velocity itself is 2 pi per unit of time. So 2 pi per second or 2 pi per unit of time is what omega stands for. So it's radians per second. So if we look below here, we can see that we have two definitions of omega, the angular velocity. 2 pi times radians per second times frequency, cycles per second, gives us 2 pi f, which is in radians per second. We can draw the same sort of relationship with degrees. Now we end up with 2 pi degrees per cycle, or cycles per second. You'll notice the cycles cancel out, and what we're left with is a measure that is given per unit of time or per second. And what is per second? The number of times that it's spinning around. So when the frequency is at 1 cycle per second, 1 hertz, the angular velocity is 2 pi radians per second. So we're going one time around, that's 2 pi around the circle. If the frequency is 10 hertz, though, the angular velocity in radians or degrees is as follows. Omega is equal to 2 pi f, 2 pi times 10 hertz, or 20 pi times the frequency. Okay, so we end up with 62.8 radians per second. If we use, instead of 2 pi, we use the degree relationship, 360 degrees times the frequency, 10 hertz gives us 3,600 degrees per second. Again, it just depends on what your analysis is calling for or what the problem is asking, whether you use radians or degrees. Now we add another factor to it. Since we already said omega is 2 pi times frequency, which is per second, if we add a factor or a unit of time in, we end up with the total angle swept by a phasor then in a given period of time. And we call this omega t. So that little funny looking w, omega, the lowercase Greek letter for omega, times t. So the mathematical relationship says that omega t is 2 pi in radians per second times the frequency in cycles per second. So the cycles are going to disappear. And we multiply that times a unit of time in seconds. Our seconds will disappear. And we end up with now a 2 pi f times t radians. So We can do the same thing if we're using degrees, 360 degrees per cycle times the frequency, cycles per second. The cycles cancel out, times a unit of time in seconds. The seconds cancel out, and now we get 360 times the frequency times time in degrees. So let's see how this works. If we want to find the angle generated after 5 milliseconds when the frequency is 500 hertz, what is the answer in degrees and radians? So let's start with the expression omega t is equal to 2 pi ft, and substitute for the frequency and the time, 500 hertz, 5 milliseconds. We end up with omega t equal to 15.2 radians. If we're solving the same thing in degrees, we have 57.3, which is the radians, times 15.7, we end up with 900 degrees. Okay, so we're looking at, with omega t, the angle swept out by a phasor in a given amount of time. A couple other examples. Find the frequency if an angle of 2.35 radians is generated in 150 microseconds. So now we're solving for the frequency. So we're going to take our expression omega t is equal to 2 pi f times t, and we're going to factor it out so that we're solving for frequency f. And in doing so, the 2 pi and the t end up in the denominator under omega t, and we then can insert our values. Omega t is 2.35 radians, and we divide that by 2 pi times 150 microseconds. We get 2.49 kilohertz. Now, if we want to solve for time instead of frequency, how much time is required to generate an angle of 75 degrees when the frequency is 1 kilohertz? So again, we move our terms around, so we're solving for time this time instead of frequency. So 360 degrees times the frequency ends up in the denominator. 75 divided by 360 times 1 kilohertz gives us 208 microseconds. So we can use either of these expressions to solve for the time or the frequency. So we go back to looking at the relationship between the circle. Sometimes we call it the unit circle, but in this case the unit itself is the radius, and we called it the peak voltage as it relates to the sine wave. Again, looking at the units of time along the bottom of the sine wave, you can see that we have some values inked in here. If we were looking at one complete cycle occurring, it says at time t initial, t0, the voltage is equal to 0 volts. And we can see that because it's setting right on the origin. And at time 1, in this case, we're going to call time 1 250 microseconds. Time 1, we're at 90 degrees. We have a maximum value, or 100 volts. So in 250 microseconds, it goes from 0 to 100 volts and back to 0 again. So if the frequency is 1 kilohertz, how long does it take to reach 100 volts? Okay, so this answer is just, well, the time is what we're looking for. We were given a frequency of 1 kilohertz. It takes 1 millisecond to get from 0 to 100 volts. If we display the sine wave on a system of rectangular coordinates, the resulting equation then for finding E, the instantaneous voltage, at any instant then is given by E is equal to the peak value of the voltage times the sine of omega t. If this sine wave represented a current plot instead, the expression is the same, except we substitute I for E. The voltage at any instant is a function of the sine of the generated angle. So you can see where we're starting, where we've been using the right triangle relationships for us to solve for what's going on the instantaneous plot of the sine wave by using the relationships in the right triangle. The voltage at the peak, which represents the vector length of the radius, E peak, is the hypotenuse of the right triangle, and the opposite side is the magnitude of the voltage at some instance of time. Again, we can look at this height as the instantaneous value. We can determine its length by whatever the unit of measure is on this axis y, and it becomes a projection from the y-axis out to the end of the vector E peak. Okay, so the relationship then, going back to the definition of the instantaneous voltage, is equal to the peak value, which is the length of the hypotenuse, times the sine of omega t. We can then say sine omega t is equal to the ratio of the projection, or the length of the height of the radius off of the x-axis divided by the length of the hypotenuse, E peak. Okay, so this is all really just right triangle trigonometry. In electronics, there are numerous ways that you can measure voltage and current. A lot of what we've been doing so far is using the peak values. The bad part about this is most of the equipment that we use to do measurements in our labs in electronics do not use the peak value. Primarily, the only piece of equipment that uses a peak value or a peak-to-peak value is an oscilloscope. So we need to learn some other measures associated with electronics, and they are given in terms of average or mean values. So when we come back, we're going to look at one of the measures called the root mean square, RMS, and look at some other ways that electricity, voltage, and current is measured when we use test equipment.